and see my screen that I'm sharing. Hello, can you hear me? Okay, Richard said he can hear me. Okay, Jeff, Emmanuel. All right. Am I audible enough? All right. Okay, so today will be our last session for our linear algebra internship, and we have some remarks from our TAs. They will share their experience also with us. But before we do that, or we come to them, I have to share or remind us where we started from and where we have gotten to. Then after that, we'll give you guys the opportunity to present your research. So I have all the research here with me. What you did, your presentation. I have them. I will upload them. Now I will enable is it a double screen where you can also interact with the screen at your end. So when I start sharing, I will enable that. Okay. All right. All right. So once again, I want to congratulate you all. As last time I said, we were 76. Now the number has now decreased, and now the maximum number that we can get to is 20. That means over 50 people. I mean, they had the eagerness to join. They wanted to study machine learning. But one thing in life that's actually, I mean, I mean, there's a saying that only 1% of people are successful in this life. Yes, it's because the 99% they are not ready to commit, and commitment is something that is expensive because one, you need to commit your time, you need to commit your brain, all these things you need to commit. But we have some people they want to, which they have the wishing, they wish, but the commitment is not there. So I want you guys to clap for yourself. You have done well. Those who are able to stick to us up to today, clap for yourself. You have done extremely well. You have done well. All right. Okay, so let me be quick so that I don't waste time because in 2 hours' time we have to end everything so that you guys can go and rest. We are all tired. Okay, it will not be easy for both of us. You learning, doing assignments, I'm meeting quizzes. The TA is also preparing labs. I'm also preparing slides, reading. It's a whole lot of, stress for all of us. All right. So this is our fall internship, and the next one will happen in February, and we'll talk about this later on. So, our main thing here is knowledge. We want to get the knowledge, and one thing I discovered uh, for the past few days is there are certain knowledge that are hidden from we the Africans, and we need to push hard to be able to, discover them. There are certain technologies that are not available to us. Okay, it's not that we can't produce things, but these technologies are hidden from us. So as a result, we watch things happen, and that is something that we want to put a stop to it, where we can also dig deep and try to do our own things all by ourselves. So our main quest over here is knowledge. Okay, we are seeking for it. So this part, when we started the internship, we introduced guys to it that we are a startup education institute with our sole aim of what training students in emerging technology. So any emerging technology, we try to train students in it. So we have our vision and also um, our mission. So our vision is to make sure we have a community of young people like you guys with what advanced knowledge in emerging technologies, and also want to create an enabling environment. That is our mission for our young people to be able to thrive well. All right, so this is our program outline. And the program outline, we are done with the first, which is the first semester. All right, and today marks the end of our first semester, which is 4 October to December, linear algebra. The next one is going to happen in February to April. Now, last time I told you guys that we have the database of all those who applied. Now, those of you able to stick to with us till the last minute, automatically you've qualified. Now, anybody who comes on again, but they were packed, but they could not stay with us, there's no way we'll give them the chance to join. And I mean, that is something that I said to myself that we are going to do. We have to let people be committed and be responsible for the action. Okay. So, those of you who are here, 100%, you've qualified if you apply. All right. And those who were not able to stick to us, when they apply, we will check their name in the database. If they are there, we'll just take them out and we tell them we are sorry, we can't continue with you because you are not able to stick to something for a very long time. So in February to April, it's going to be calculus and optimization, and I've already started preparing the slides, everything, and it's so fun. It's so fun, and we will put in a lot of, I mean, arrangements, a lot of, I mean, uh, programs and a lot of activities to make sure that whatever you guys requested for the feedback, I've gone through the feedback and I've seen that some of you were suggesting certain things. We will make sure we address those issues and challenges so that the calculus and optimization one will be fun and it's going to more yeah, fun. Then the last one is going to be June to August. We'll talk about that, but the one that we should focus on is the second semester one. All right. So then I just want us to take this, I mean, time, opportunity to say big thank you to our TAs. Please clap for them. Let's clap for them. Let's clap for our TAs. Let's clap for our TAs from Sameh, then James, Anaya, Harry, Cecil, Irama, and our Charlotte. He has been, or she's the one who is sending messages on our platform. Then Jeff is, let's, I mean, clap for them. They have done well. They've done well, right? Now, they have their personal agendas, but they were able to sacrifice and help us with the training, prepare the lab. Some of these things, I mean, it takes commitment. So please, let's clap for them. Let's clap for them. They have done well. They have done extremely well. All right, they've done well. Okay. All right, so I don't want to waste time. We are going to start our presentation, and I share the presentation order in the chat. All right, so this is our presentation order, so which we have 7 teams here or 7 groups over here. All right, so I'm going to upload your slide here. Okay, then I'll enable so that you guys be able to interact with it and uh, present. Last time, as we said, we you have only 7 minutes. Okay, because you don't have a lot of time. You have only 7 minutes. Okay, so as I said, the introduction, your problem statement, then your methodology. Your methodology, as I said, that is where you need to spend more time and tell us, I mean, what you came out with, okay, using all the things you've been taught over here. Now, as I said, the best projects, I mean, work will be announced, and also the best student also will be announced. Then the most punctual student also will be announced. Then the most active student also will be announced. Okay. Now, the projects, some of them, as I said, is publishable. We can publish it, work on it, and turn it into a project that if you are even in level 300, going to level 400, or level 200, going to level 300, we can work on this project so that you can publish it and present it during your final year. Okay, so we'll look into that if we see that your work is something that we can publish. All right. Okay. So let me stop sharing my screen. Then I'll give you guys a go ahead to show team synergy. All right. So get ready. I'm going to upload your slides right now.
Everyone. I'm Inshira and I'm the presenter for Team Synergy. The topic for our project work is movie recommendation system using cosine similarity, and these are the team members. This is our presentation outline, so we'll begin from introduction, then to problem statement, methodology overview, then we'll conclude. This is a picture demonstrating a lady interacting with a movie recommendation system. Some of us use apps like Netflix. So when you open your Netflix app, you see that it suggests movies to you. And when you watch them, you end up liking them. You ask yourself how. It's due to something known as a movie recommendation system. So what is a movie recommendation system? It's a system that suggests movies to you based on your interest or the movie content. So some characteristics of a movie recommendation system is that it's content based. What this means is that a movie recommendation system depends on the features of the movies. Examples of the features are the titles, the keywords, and others. And also, our recommendation system uses a concept known as cosine similarity. Problem statement. Why did we decide to do this? For example, the movie data set we use contains 5,000 movies. So if you are going to go through this data set manually, you'll be overwhelmed, you'll be stressed. And before you get a movie that you like, you'll be stressed. Yes. And also, we want to solve the problem of traditional systems that rely only on user ratings. That is also known as the cold start problem. So our goal is to build a system that understands movie content and suggests relevant titles without needing any user history. So this the steps we used in making or creating our movie recommendation system. So we collected movie data from Cargo, that is a TMDB data set. And as I said earlier, it contains 5,000 movies in its data set. And afterwards, we extracted key features like the genre, the title, the top cast, the crew, because it's not all the features that were important. Then afterwards, we converted features into numbers using text vectorization, which is TF-IDF, which stands for term frequency, inverse document frequency. We know that computers don't understand text directly, so we had to convert it into numbers. Then afterwards, the cosine similarity between movies was calculated so that the similarity between the movies could be known. Then afterwards, recommendations were generated. So why did we use cosine similarity? Um, it's because it depends or it's based on direction, not magnitude. So it depends on the angle between the movies or between the vectors, not the magnitude. It does not depend on how large the magnitude, how large the description is. Yes. Also, it delivers fast and scalable matching. This is the formula for the cosine similarity. Cos theta is equal to a numerator of the dot product of vector A and B all over a denominator of the product of the norms A and B. So finally, we are concluding. So what were we able to achieve? We were able to achieve a working movie recommendation based purely on content, no user ratings. And it's fast and accurate and it uses cosine similarity. And we deployed our app using Streamlit. So it's deployed. You can actually So why it matters? It helps users discover movies they will enjoy without endless searching. So as we said earlier in the problem statement, users find it very difficult going through thousands of movies to get a movie they will love. So we help. It helps to discover movies easily, and it demonstrates the power of simple machine learning techniques in real applications. So these are the links. The first one is the link to our movie recommendation system, and the second one is the link to our GitHub repo. So what we've been saying so far is behind the scenes of our movie recommendation system. Yeah, thank you very much. So please, I'm done. Thank you.
thank you, Inshra. Thank you. Okay.
It's the comparative study and analysis of dimensionality reduction techniques. Now the introduction. In machine learning, we are most machine learning practitioners are often confronted with high dimensional data, and this high dimensional data is only is only a part of it that contains the necessary information, while the other parts consist of just noise and things that are not necessary. And so many techniques have been used to reduce the dimension of the data so as to extract meaningful information without the high dimension being a problem. Now, based on the work performed by Velingri et al., they examined dimensionality reduction in terms of computational efficiency and noise attenuation, and they were able to bring out how useful it is, the advances it has brought about. But irrespective of this progress, the a comparative evaluation of it a is still a challenge in the field of machine learning. So because in comparing these algorithms, each algorithms optimize a separate portion. They try to some they try to optimize the neighborhood preservation, while some it's the global structure that they try to optimize for. So but a recent research that is being done by Rastogi and the others, they advocate for a multi-criteria evaluation framework that combines reconstruction accuracy, neighborhood preservation, and computational efficiency to assess the quality of transformed feature spaces. And that is where our work comes in, because we our study contributes to this by bringing about a controlled end-to-end comparative analysis, and we use three data regimes: linear data that has been synthetically generated, non-linear data also, and semi-linear data, which is so as to mirror real-world data set. And we evaluated linear and non-linear method across target dimension, and we picked the best out of this to compare them together on the mixed data sets. So our problem statement, the main question we are trying to answer is, how do linear and non-linear dimension nitrogen reduction method performs when their assumption. Hello. Okay, so how do linear and nonlinear dimensionality reduction method perform when the assumption align with the data generating process, that is the underlying structure of the data, and which algorithms generalize best under semilinear conditions, which mirrors real world data set that is not 100% linear or 100% non-linear. So, and which metrics reliable capture the reconstruction fidelity and structural preservation across varying dimensions. So, we believe that addressing these questions is going to guide practitioners in selecting DR techniques, and it will contribute to knowledge. So, our methodology? Our methodology involves several stages. First is the data generation. Like I said, we made use of three categories of data, all of which are synthetic data. We did not make use of real data set, and I will further explain why we did that. Now, for data generation, we made use of linear data sets that was being generated. We augment it with Gaussian noise and made use of correlated features just to expand the number of dimensions. Then we also used nonlinear data sets using Swiss rule, and we made use of semi-linear data sets, a combination of linear and nonlinear data sets to mirror real world data sets. That's the first aspect. Then the algorithms that we evaluated, the linear methods we picked the most common ones, and we choose PCA, incremental PCA, truncated SVD, factor analysis, sparse PCA, and the others, as you can see from my slide. And even though this is not too exhaustive, but due to computation limitation, and we just pick these ones as representative of the others because of how common they are being used. Then the non-linear methods that we also used, as you can see on my slide. So we only picked five out of them. policy that we used in creating a reconstruction, because if you want to have a if you want to measure the reconstruction error, then reconstruct the original data set to use in measuring it. So or for our work, we made use of just the NumPy library and scikit-learn. And for the methods that already have a implementation for the inverse transform, we used that to generate the reconstruction. While those that don't have, we used Penrose inverse to generate the reconstruction of the data. So that's for the reconstruction policy. Then the evaluation metrics, we evaluated them based on five metrics: Frobenius norm, relative Frobenius norm, for scaling the normalized to for its normalized errors that is scaled. Then we made use of spectral norm, mean absolute error, and reconstruction error. Now you will notice that out of all these evaluation metrics, we did not make use of other metrics that are being used for non-linear data set, because what we are majorly trying to measure is reconstruction error. So that is why we made use of just this particular metrics, and we did not use other more common metrics or neighborhood preservation metrics. So that's on that. Then the whole workflow of our work is that after we generate the data for each data set, we fit it on the algorithm, we compute the embeddings and then reconstruction, then we calculate the metrics, then we aggregated the results. So that's that on our clinic. So what were the results that we obtained for the linear data sets? On just the pure linear ones, PCA truncated SVD have the highest reconstruction behavior that we observed. And SPCA also tried. While for the non-linear, we had isomap spectral embeddings. So those were for them. Then on the semi-linear, where we picked the best three in the two, where for the linear ones, PCA and truncated SVD performed very well. They dominated even in that regime. So while for the other one, isomap did very well. So what were the key insights that we can draw from this for construction and compression? PCA or truncated SVD was they were performed very well for reconstruction and compression. Now for in choosing between linear or semi-linear data, increasing the K represents the number of dimensions near intrinsic, uh, increasing the value of K, the number of new dimensions. If it is close to the actual underlying structure, the actual ground dimension, it yields a better result. And for nonlinear manifolds, isomap is best to balance geometric preservation and reconstructability. But because our focus is only on reconstruction, so it is still okay. And the conclusion we can draw from this is that for real-world datasets, semi-linear data combining a strong linear method with a robust non-linear method offers complementary strength. They complement for each other because non-linear methods they perform well in preserving the geometric structure, while the linear methods they work well in reducing reconstruction error. So this can help practitioners in deciding the best dimensionality instruction to pick for on depending on the data they are working with. So these were the R2 score that we got for it because our work we made use of a dimension of 12 dimensions, but the underlying the ground truth, the main dimension of the data is actually five original dimensions. The other seven dimensions were just noise that were added. So, and we try to measure the R2 score based on a reduced dimension. We first of all reduced it to 2 dimension, then 4 dimension, 6 dimension, and 8 dimension. So for each of these dimensions, this is the result of the R2 score that we obtained for all of them. And this shows the graph for the mean absolute error and the R2 error. So even though there are other ones, but we couldn't add everything to the slide just for space and that's all. But the link to the GitHub repository can also be provided. So those are the papers we consulted in our work. Thank you. So for the link to our work, I would put it on the group chat now. I would.
Okay. Uh, Hello. My name is Godwin, and I'm presenting on the image compression using with SVD. So, first of all, SVD was first established by real square matrix in 1870 by Beltrami and Jordan. It's a powerful data analysis tool that can be used in signal processing, statistics, and machine learning, amongst other fields. So the problem that we notice is that high dimensional image, every image that you took on internet or you take naturally is expensive to store and then and process. And we notice that the image has high, although the quality is good, it has high, it takes high memory. So we, and also in many images, there is some redundancy of information. And for example, if you break the image into a square matrix. So what SVD will do that is to provide a principal way of to compress that image with a minimal loss of the quality. So what is the SVD? Our method first is to upload the image from Google. I use Google Scholar, and the image that is exploded are same images, scanned electron microscope of pollen and melanin foam. So the first of all, I request the image, then I use Python libraries such as computer vision library and Python imaging library to upload and save the image and then convert it into an array of integers. So the basically the image is then presented as a matrix, and then we use the SVD factors such as the U, which is the left singular, which contain the left singular vector, and then the the singular vector, and then the right singular vector. So So after I'm done with the decomposition, I did some calculation, which is I calculated first the variance explained, and this variance explained is what does it give us is it gives us the fraction of the total data variability that is captured by a given component. So the same image, what I when I use this variance explain formula, and I've been able to plot the singular value, singular vectors against the variance explained of each of the component data I take. So in total, the same image of pollen contain variance singular vector of 355, and then the second plot contains 1070 singular vectors. So after I also I calculated the relative error, the compression ratio, and the approximation. So hello, okay. So from the result, I plotted the related error against the k value. The k value is the number of components. So we see that from the relative error, as the k value is inversely proportional to the relative error. So it's as the k value increases exponentially, the relative error also decrease exponentially. But for the k value, the number of components chosen, um, we have a proportionality between the k value and the compression ratio, meaning that the k value increases proportional to the compression ratio. So So we are plotting that I can say that each singular value contributes to a total variance, and then the steeper the curve means that most information is being captured by a few components. So in my case, I got the component for the k value for the figure one. For the figure one, I got the same image of pollen. I got my, you have been able to retrieve most of the information at a component of 35. And then for the melanin foam, I was able to extract got a good quality at k is equal to 50. So in conclusion, what can we say? In conclusion, we can say that the SVD is an effective tool for image compression and analysis. And then variance explain also quantify the information that can be preserved. So the method is also applied for signal processing and in machine learning. And the other application of the singular vector, uh, um, and other application of the SVD can be solving system of linear equation, a homogeneous system, and determine the dependency and near dependency. It's also helped to remove redundancy and then get rid of unnecessary data. Thank you. So I got my information from this my reference. I got the information from the NumPy documentation, and then the SVD, and an article on the singular value decomposition. And this is my singular value decomposition image. I got it from this. Thank you. Hello. Thank you.
Thank you. Okay. Any question for Godwin?
Okay, so this is the RBT group and it consists of Tomasia, Richard, and Bessie. So our topic is heart failure prediction using machine learning. So heart failure is a heart condition where the muscles of the heart is not able to pump blood and oxygen to other organs and other parts of the body. And then it also has a leading cause of global mortality of about 17.9 million deaths annually. And also, current risk prediction methods are limited by their reliance on traditional statistical approaches, which fail to capture complex interactions in large multidimensional data sets. So, so some predictive models, particularly machine learning based ones, offer promising solutions to predict risks of adverse outcomes such as mortality and also hospital readmission. So some models such as the random forest, the classifier, the multi-layer perceptron network, the naive and logistic regression are some of the commonly used ones so far. And so what is our proposed solution? So our proposed solution is a heart failure prediction model that predicts survival outcomes using linear regression. And also doctors and cardiologists may use this model to easily predict heart failure outcomes based on patient data. And Richard will continue from here, please.
So yes, for our data acquisition, our data was obtained from Kaggle. Kaggle, as we all know, is a popular open source platform that provides public data set for machine learning and data science initiative. Our data file was named Heart Failure Clinical Records dataset.csv. So as you can see, it's a CSV file, so it was easy to use Python libraries like pandas and NumPy to load and analyze it. So our data was obtained from Faisalabad Institute of Cardiology and the Allied Hospital in Faisalabad, that's in Pakistan. We chose this data set because it is widely used in research for classification, risk prediction, and other heart diseases related machine learning tasks. Next slide. So after obtaining our data, the next step was to do an exploratory analysis on the data. So we use Python libraries like NumPy, Pandas, and Matplotlib to load the data, explore, clean, and visualize the data. So upon our exploration, we found out that our data consists of 13 labeled columns and 299 rows. So with these 13 columns, it consists of 12 features and the one target. So that the target is a death event. The 12 features, as you can see on our screen, is the age, anemia, and other features. So after this, we had to visualize our data using the library Matplotlib. So we visualize we did a graphical visualization of our data. As you can see, age is a continuous feature. That's why it has so many bars over there. But anemia is a binary feature. So it's either you have anemia or not. And also for the graph on our far left, it is evident that our data has more survival rates as compared to the death rates. So the next thing, we also try to visualize the data using a correlation heat map for all the features. And also looking at the graph at our far left, it's a box plot of our data. So you try plotting the age against the death events. And as you can see, the higher your age, the higher the chances of you dying. And also we plotted time against death events. And the time here is the time you visit the hospital. So the higher the time you visit the hospital, the higher the chance of you surviving. So Bismarck could take on from building this model.
All right, so right from there, we proceeded to build the linear regression model. So I'll take you through the step-by-step process. Yes, so first, what we did is to split our data into two. One will be the feature matrix, and then the other our target, which is the death event. So we realized that most of our features or some of the columns, the data that we have there are very huge. So example platelets, they were very huge numbers. So the next thing we did was to standardize those features. So after standardization, this is what we have. All right. So our third step was to add the bias column or the intercept column. So we added columns of ones, as you can see. So once we run it, we had this. So you can see ones being added. From there, we went on to solve the normal equation, as you can see. So X is our feature matrix, Y is our target, and then B is the coefficient matrix that we are trying, or the coefficient vector we are trying to find. So to do this, we pass through a certain number of steps. The first one, if we recall, the shape of our matrix is 299 by 13. So the first thing we did was to transpose it. So when we transposed it, we had 13 by 299. And then next, we want to get a square matrix so that we can find its inverse. So we multiply the matrix, our feature matrix, by its transpose, and then we had a 13 by 13 square matrix. And then we went on to find its inverse, and then finally we solved the equation. So once we solved the equation, we obtained our coefficient matrix from we have 13 coefficient from B0 to B12, where B0 is our intercept or bias, and then the rest follows as we can see on the screen. So next, we try to verify if our inverse method gave us the same result as the least square method using NumPy. So when we did that, we had a match. So we had the same result as the least square method. Then we now moved on to our final equation. So we have our model here predicting survivor events. Right. So after that, we then try to test our model to see if it will be able to predict. So what we did was to create a NumPy array containing all the features, all the 12 features. So for this, we tried for one survivor event and then one death event. Then what we did was that because this is a continuous, the linear regression model gives a continuous prediction, whilst our output is categorical, that is 1 and 0. We cap it at zero point 0.5. So if the prediction is greater or equal to zero point 0.5, we approximate it to 1. That's a death event. And if it's less than zero point 0.5, we approximate it to 0. So we did for one survivor event and then one death event. So as we can see on the screen, we can see a continuous prediction and then the predicted death event. So he was able to accurately predict. So after testing the model, we went on to find our metrics. So the metrics here were actually three: the mean square error, root mean square error, and R squared. But because the root mean square error is just the square root of the mean square error, we skipped that one. So we had a root mean square error of 0.3565. So this is how far the prediction is from our actual prediction. And then the R square value, we had 0.4168, which means that only about 41.68% of our whole or entire data set was used for the prediction, whilst about 50 something percent is noise. So we can conclude that our data is a bit or is very noisy. All right, to conclude, we can say that the team was able to predict the survival rate of heart failure patients using linear regression model. And then we were able to successfully implement the concepts of linear algebra we learned during the course of this internship. And then one thing we also realized was that linear regression models, our linear regression model had a lot of noise. And this is also consistent with some research that we found online that linear regression models are not very good for classifying categorical data. And so we look moving forward, we would like to use other classifiers like the logistic regression, k nearest neighbor, among others. So these were our references. And then we've added a link to the Kaggle notebook we used for this project. And thank you. So this is the end of our presentation.
All right, thank you guys. Please just clap for them. You've done well. Any question from the TAs?
Can everyone hear me? Good evening. This project is called Color Blindness Simulation and Correction Using Linear Transformation, presented by Team ACES, which is me, Manal Abdulkad Mohammed, Esther Precious Amlon. Now, human vision is trichromatic. That means that our eyes rely. Oh, I'm so sorry. Our project is about simulating and correcting color blindness using linear transformation, as the title suggests. At first glance, it looks like a vision or an ML problem, but at its core, it's actually a linear algebra problem: vectors, spaces, projection, and null spaces. Now, human vision is trichromatic. It's a tongue twister. That means that our eyes rely on three types of cone cells: L, M, and S cones, which respond to long, medium, and short wavelengths. If you think in linear algebra terms, these cones act like basis vectors for how we perceive color. So effectively, our perception of color lives in a dimensional subspace of the electromagnetic spectrum. If one of these cones fails, it's not just less color, it's like losing an entire axis in a coordinate system. Computers approximate this biological system using RGB. Every pixel in an image is literally a vector in three dimensions, just three numbers. Image processing then becomes very simple conceptually. We apply matrices to millions of these vectors. So when we say image correction, what we really mean is linear transformations applied at a scale. This slide is not showing. Okay, now the problem, dimensionality collapse. We focus on deuteranopia, which occurs when the M cones, green sensitive cones, are missing or defective. From a math perspective, this means that the green axis disappears. So the original 3D color space collapses into a 2D plane. That's why red and green become indistinguishable. These vectors now project to the same point. No amount of turning up the green fixes a missing dimension. Now, this loss is mathematically a linear projection. It creates a null space. So every projection creates a null space, directions where information is permanently lost. I'll get to null spaces later. Any colors that differ only along the Mrs. Green axis lie on what are called confusion lines. Once projected, they collapse to the same value. This is why color blindness cannot be reversed. The image is simply gone. Now, our approach to model it correctly, we implemented a four-stage pipeline that mirrors both physics and biology. Each stage is necessary. Skipping it will result in something that breaks the mathematics. The first approach is linearization, removing gamma correction to restore physical intensity. Then the basis change. We convert RGB, the red, green, and blue, which to LMS, the cone response space. Then transform, apply linear transformations. Then lastly, gamma, we reapply the gamma for display. Now, most images are stored in RSGB, which is standardized red, green, and blue, which uses gamma compression. This makes pixel values nonlinear with respect to light intensity. Linear algebra doesn't work in a nonlinear space. Adding two sRGB vectors does not correspond to adding light. So the first step is to linearize the image by removing gamma correction. We restore the physical meaning before applying the math, and this is the formula we used. Now, step two, change of basis. RGB is a device dependent basis. It's about screen phosphors, not biology. To stimulate human vision, we change basis from RGB to LMS, which corresponds directly to cone responses. We use a well established transformation matrix from Bertel et al., which is widely cited in vision research. And this is the matrix we used. Now, the simulation matrix. In LMS space, deuteranopia is modeled by projecting the M cone axis onto a plane defined by the remaining cones. The M cone is replaced by a weighted combination of L and S cones. We then combine these transformation into a single composite matrix, which makes the computation efficient. So now we get a composite matrix called MSIM in our cargo notebook. Now here is the null space. Anything that originally lay purely along the green axis now maps to 0. That is why direct correction is impossible. We need a different strategy. So instead of trying to recover lost information, we redistribute it. We compute the error vector between the original image and the simulated colorblind image. Then we shift this error into directions the viewer can still perceive, mainly the blue-yellow axis. This preserves contrast and improves distinguishability without violating the physics. And this is the formulas we used. Now, the Python implementation, we use NumPy and vectorized operations. Rather than looping over pixels, we simply replace the image into an n times 3 matrix and applied one matrix multiplication. And here is what our slides, our cargo notebook produced. Normal vision, the simulated deuteranopia, and then the corrected daltonization. Now, it might look weird. Give me a few seconds, I'm almost done. It might look weird. This is what a normal vision would see, the sunflower. And then in the simulated the deuteranopia, it becomes this weird reddish color. But the problem here is that it's a bit hard to differentiate between the petals and the surroundings, and that's the problem we are trying to solve. So in the daltonization, we created some sort of blue-green implementation here for colorblind people to see. These images are exaggerated for the computer to understand. And so now this project shows that many machine learning and vision problems are fundamentally linear algebra problems. By respecting physics and biology, linear transformations alone can simulate and improve color perception. Machine learning starts with math, and this is one of those cases where math does all the work. And that's a link to our cargo notebook. Thank you, everyone. You're done.
You, any question? Any question for the group from the TAs? Any question? Wow. Okay. So yes, the mathematicians and the physicists and the biologists are trying to use linear algebra. All right. So this is also fantastic, and I love the presentation. To be honest. All right.
Good day, everyone. So the my project is actually predicting a senior high school food budget using linear regression. Like basically, it's about um like to determine the weekly cost or like a weekly cost of what a senior high school student spends on like the weekly cost of what a senior high school spends like during a week, like what a student spends during a week. So here is the problem statement. Like to predict the weekly food budget of a senior high school student, as I said, using so we are going to use those. What we are going to use now is going to be the what a person will obviously like spends daily, maybe during the week, like on rice, eggs, bread, fruit, and water. That is what we're using. And we're going to like build a model using linear algebra. So now the linear regression model, we assume that the total budget is actually a linear combination of like y being equals to w naught plus w1 times x1 plus w2 times x2, then dot 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 like to wm times xm, where this xi is the cost of each food item, and weight here is talking about like how each of the food items listed affect the weekly budget, which is y in during the week. Like the weight is how each of the food items affect the like either increase the food budget or reduce the weekly increase his weekly spending, like the budget, like the y which we are trying to find his budget, or decrease it. So the w naught is actually the base weekly budget he like the person spends. The person is like meant to spend on a normal. So now in the matrix representation, I'm sorry for not putting the matrix in the in the slide, like actually. But okay, let's just go with what we have for now. So we have that y, which is the total food budget. Like total budget he is going to need for the week equals to x dot x dot w. That's like the dot product. So where x contains all the weekly food costs, like the cost of all the foods according to like the eggs, the rice, which we are going to use like to determine his budget, the student budget for the week. times the weight. As I said, weight is how each of all those food items affect the budget. Either it goes up or it comes down. And why is what we're trying to find, which is like the weekly, what he spends like weekly on, like on his food. So now finding the best weight, we're going to use um to find the weight, we're going to use that x transpose dot x raised to power minus one, like the inverse of this, like the x transpose times x, then times x transpose times y. This is to actually to minimize the mean square error, like so that to reduce, because the lower the mean square error, the more better the model is to going to predict the his weekly his weekly budget on what he spends like weekly on his food. Because the lower the error, the more accurate the model tends to be. So now, what do we mean by weight? As I said before, each weight shows how strongly an item affects the total budget. So if the weight of rice, for example, is two, so for every 1 unit of rice, of every 1 unit increase in rice, it adds 2 units to the total budget, as I said. So example now, if for example now, if this weekly right, like if this weight, if the weight of rice was three, you will find out that for every 1 unit of rice, maybe in the why we the model, if if 2 units of rice were to added, you find out that it will be like 6 units. It will be like six. The cost of rice will be six added to the total budget. Like this means that it will be increase the total budget. So now the weight, as I said before, is what the is how each of all these each of all these what did I say? Each of all these um right, all these his weekly, what he spends his money on, like rice, the eggs, and every other thing affects the his weekly budget. Why doubly not, as I said before, is the starting or base budget he is meant to like spend on the normal. So now making the prediction for the new weekly food cost, that is for his like the model, like what the model uses, what the model will actually use to make the prediction. Now we have that, why why not? It's going to be X new. X new is actually now going to be with the weights added. Like for all those for all the predict for all the wait, excuse me, sorry. For what the all the like all the cost for X new, X being the what he spends his money on, sorry for the glitch. X being what he spends his money on times the weight of all, like for maybe it can be, for now, yes, it can be X times his weight plus like the whole equation being from the beginning, like this first equation that was represented here. Sorry, yeah, yeah, using this first equation, but now with all the weights being like after it has implemented the mean square error and every other thing. So this is what is now going to use to build the model. Yeah, this will now give the predicted weekly budget of the for the that a senior high school student will spend weekly. So thank you. I'm done. I only focused mainly on the math aspect. I didn't actually the code was, I didn't add the code to the slide because we had to only focus on the math aspect, because even during classes I will always do the maths, then we have our lab session different. So I didn't actually add the code, just focus on the math aspect of the this thing, the of the project. So thank you. I'm done.
All right. So, Iman, that is fine. Okay. Well done. Okay. Let's clap for him. All right. Well done. Taking something like this and trying to um, model it mathematically. And this code that you spoke about, these coding things, they are all from maths. So if you can write the maths, you can write the code easily. All right. So that any question for him?
For your patience then. My name is Auda Nansafiano and I work with Sen Charlotte brain tumor detection using image compression, sorry, that's SVD. So first of all, a brain tumor is an abnormal growth of cells in the brain. It can be cancerous or non-cancerous that potentially affects the brain's function. So our problem scoping is MRI scans usually provide clear, non-invasive brain tumor detection. Diagnostic challenges usually include high dimensional images, varying tumor shapes, then manual radiologist interpretation. Using applying SVD, SVD usually compresses the image, only keeping the most important parts, then accelerates detection. Then, okay. So as you apply SVD to the images, it reduces data complexity, preserves essential tumor features, then enables faster detection and treatment. So our main objective is to develop an efficient way to detect brain tumor and facilitate its fast treatment. So our methodology, we use mathematical tools like SVD, matrix algebra, linear transformation, then SVM. Our technical stack include the scikit-learn, NumPy, MATLAB, Matplotlib, PLI, Open OpenCV. So our methodology, first of all, you load the data. I'll upload the link to the Kaggle after. We took our data set from a brain tumors. So first of all, we upload the data. This includes pictures of brain scans, normal and ones with tumor too. Then our second step, we pre-process the images. That's we resize the images to 128 by 128 pixels, convert it to grayscale, then normalize the pixel values. Then we apply the SVD. So here's the formula we use to apply the SVD. Then now we are building our classification model. So first we divide the data into features and targets. Then we train text split, then standardize features. For training and evaluation, we used a confusion matrix. They will calculate the accuracy, the precision, the recall, and F1 score. For the interpretation, a high TP would mean a good tumor detection. A low FN means few tumors were missed. A low FP means a few false alarms. That's uh, no detection. That's no tumor, but the machine detected a tumor. Then high TN means good normal indication. Our result and interpretation. So that's what I was talking about. The accuracy, precision, recall, and F1 score. All all indicate the result of our SVD. Then now we are visualizing the results. So for the visualization, we can use in the code itself, we use a PCA where the dots are on the graph. So if you check the code itself, you see then we use the correlation there, then you understand how the results were visualized. So from observation, low rank approximation preserves tumor features. That's if yeah, our K is 50, so that it reduces the size of the picture but preserves important features. So when you are giving it to the model, it will detect if there's a tumor or not. So then our conclusion, uh, benefits, it provides visual explanation, easy to implement, and reduces data storage needs too. But for our limitations, the key the key means the key value usually indicates whether important features are kept or not. So you have to be careful with that. Then also the image quality which we uploaded before it will be compressed. Then of course, even though it's a machine learning something, but it can't actually replace the professionals too. So we have to be careful with that. Then for future work, we can actually implement it in multi-resolution analysis, color MRI, then growth tracking over time too. Then here's our reference. Then thank you very much. That's our project.
Yeah. Um, I wanted to just see how um, impressed is too big, but it's how impressed I am with this whole internship and all of that. I learned ML in a different way, and this whole thing was and it was a learning experience for me, almost like I was also doing the internship with you guys and having to go through the slides and prepare for the lab session was all learning for me, and I just want to encourage you all to not give up. Just continue exploring, continue going deeper in this whole ML thing. The projects that I did, they so exciting projects. I really loved the one on the eye. Had to go and read around it while you're presenting, even to get more details on it. I think some of the projects though were you were was oversimplified. The problems you're trying to solve were much bigger than with the approaches you were trying to solve them, trying to tackle them with. So just like I don't know if maybe you didn't give you enough time to prepare or you didn't know the stuff, the concept, so you're unable to get projects that will like hit it right. It's like some of them were um, oversimplified to fit what you wanted to do. But then aside that, everything was nice. It was nice. It was nice. It was nice watching and learning from you guys. And just want to thank Richard also for this opportunity. And I learned so much, and I'm looking forward to the next one. See how we can also help in that one. So perhaps maybe that one I'll be a student on that one. Yeah, so thank you very much. And that'll be all from me.
Um, hello everyone. This is Samuel. So I just want to uh, uh, congratulate um, whoever joined the internship and then was able to make it this far. This will like proves that's like we are really putting the commitment and then the edge to make a very very positive change. So with the project that were presented, and then throughout these weeks that we've gone through the course, right? Like even for myself, it has given me like a whole new perspective as to like how we are to go about machine learning and then like AI as as a whole. So like for us to like really gain control, like trying to like use all these fundamental concepts in linear algebra to um, to do this project and then like explain like the background of it is like very encouraging. And then I'll just urge us to learn more, and then to also pay attention to every bit of advice that say used to tell us. You know, like Mr. Selma is having a lot of experience, so
all these bits and pieces. I mean, the whole narrative that like he's trying to push for us to also like go through. It's a very good course, and then like if we like pay attention to it and then work towards that, we will really make like a large impact. So that's all from me, and thank you very much. Yeah.
Okay. Hello everyone. So this is James here. I'd like to congratulate all of you two for the very good work done. I think Jeff and Samuel have said it all, so no need to repeat that. So I think I look forward to seeing you next semester. Those of you that are really interested in this, just keep learning it. And also, let's really appreciate Mr. Siama for putting this together. It's a lot of work. So he's done really well in putting it together. So thank you very much, Mr. Siama. I think I've also learned a lot within this period. Okay, so I look forward to seeing you next semester. Congratulations again.
Hello, sister Nana, yeah. If you're on the call, can you go on? Any of you?
Yes, yes, yes. Yes, so yes, actually, everyone or most, if not most of you, actually did pretty well. I was impressed by some of their presentations, and they gave me some form of reinforced hope that very soon we Africans too will be coming up with our own, like, actually novel machine learning and deep learning algorithms, right? All derived from just making a small change in the mathematics that goes behind implementing the respective algorithms. Yes. So yeah, I also was particularly impressed by the project on the color blindness. Yeah, like the I personally have never really come across something of that sort, but seeing the approach that was used to actually address it, yeah, it was actually impressive. Yeah, and I'm not trying to say, I'm not trying to downgrade the other projects, but the other ones were also very, very, very good. Yeah. So well, we all everyone did well. You guys did very well. And I also hope to see you, most of you, or in fact all of you, if possible, in the next in the next semester. Yeah. So yes, thank you very much. And also, I'd like to say that it was also a learning experience for me, because I actually got to learn a lot of things. I've been dealing with a lot of machine learning and deep learning models for about the past 2.5 to 3 years. Even though I had some idea about the mathematics that went into, like, the basic machine learning models, like linear regression models, logistic regression, support vector machine, so on and so forth. I didn't really know the exact, like, the basic form of mathematics that went into them, like simple linear algebra and all those stuffs. Yeah. So yes, this 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 course actually opened my eyes to a lot of things, and it made me see how understanding the mathematics takes you a step closer to actually developing your own novel algorithms. Yes. And so yes, it was a learning experience for me, and I also hope to sometime apply what I learned from this course, and also hopefully, who knows, I may also come up with my own novel, efficient and working machine learning algorithm. So yes, thank you very much, and thank you guys too.
Can you hear me?
Yeah, Ahmed, I can hear. Go on.
Yeah, I was having issues with my network, so I didn't actually um hear what he said. But I think maybe he just wanted some words from us, if I'm right. Can you hear me? Okay,
Yes.
okay, all right.
So, all right, I would just like to say thank you to everyone. And personally, I joined late, but when I joined, the few things I was able to pick up, I think was good. And I would like to thank Mr. Isiama for that. Since I met him, he has been so good to me, and then he has been pushing me and all that. And I think he's someone that each and every one of us can learn a thing or two from if we are really serious and we are ambitious and we are really serious to learn. He's going to push us and he's going to give us that opportunity to learn, and we are going to get to new heights that we might not even think that we can get to. But with Mr. Siam, I'm sure we'll be able to get there. And I'm looking forward to seeing you all in the next semester come February next year. Thank you.
All right. Thank you. Thank you. Is Nanaya on the call? Nanaya, are you here? Maybe the network. Oh, all right. So, Rama also sent me a message that she won't be around. She's also at a conference now. So, I wish she was here to say something. All right. So, that is that from our TAs. Okay. So, guys, you remember when we started, we said we'll be giving award. Now, you your certificate will be sent to you, but one thing I want to say is that your focus should not be on the certificate. Yes, it's good to get the certificate, but someone said the result is what matters. It's not the certificate. The certificate is just paper. But if you can do something, that is what is important. You understand? So the application of what you've learned is what is important, not the certificate. The certificate can open doors, but what is going to keep you and it will network you to other people, or other people will see you. Okay, so it will be sent or it will be shared with you guys maybe next week or before Christmas. Okay, and some of you, I ask you guys to fill the form. Please, we need the feedback. You've received some of them. Please, I'm just pleading. Please provide this feedback for us so that we'll be able to, organize the next one much more effective. Okay, we can do that. All right, and lastly, some of you, the project work, as the TA said, they are all fantastic, but some of them we can take it to a higher level. So when we are done, we send mails to some of you where we will take the project work and build it. Okay. Now I know next year, which is next month, school will resume, pressure will come. Yes, but we are still going to get some of this work done. So please get ready if you receive a mail from me that your work, we want to take it up, okay, to a different level and get it published. Right now, as I'm talking to you, we are working on a paper to get it out. So make sure if I send you a message, get ready. I know it's going to be tough for you combining schoolwork and also this, but we need to get it out. If you don't get it out on time, okay, we will, the fire or the motivation will quench and we'll be able to get it out. So get ready if you receive any mail from me that you are going to work on your project. All right. So the last thing is the award. Okay, remember we said that we'll be giving award to some of the students. But before we proceed, I want to give the participant two or three of you to share your experience. Just go on and share the experience with us before we proceed to the award. So any of you can unmute and just tell us something small, maybe 30 seconds, what you learned, what you hope for, okay, the next internship, okay. So any of you can go on, okay, two or three or maybe four or maximum five, let's say five participants. All right, so the floor is open. So the award one, I wish it was form of, but the time will come. I mean, it's going to be a tangible stuff. And if I say tangible, maybe you'll be remunerated. I mean, some money or those things will be given to you, or other stuff. Okay, but now it will be a certificate. So we'll write on a certificate that during this internship, you were the best, you were the most punctual, the best project, and all these things. Okay. So the first one we want to talk about is the best student. Now, the best student, we talk about the quizzes, okay, the lab submission. All right. So we collated everything, we put everything together, and we pick the highest score. The highest score. The highest score we had, some people had A. I mean, on Canvas, normally grade you using A, and A minus and all those things. But we picked the highest score. We had about 5 people scoring A, but the highest of them all is what we chose. And the best student goes to Godwin. Godwin. So let's clap for him. Okay, let's clap for Godwin. Okay, he did well. Okay, actually, I mean, I've been studying him. Okay, in terms of assignment, all these things, you see that the guy is on time. Okay, what I'm saying that 5 people had A, but he had the highest score among them all. So Godwin, congratulations. Okay, keep it up. Keep working hard. Okay, let's stick together. And I know, I mean, you have potential. You can do something great in the next future. All right. So the next thing is the most punctual. Okay, the person immediately we join the call, you see him or seeing him or her, okay, on the call, and he doesn't joke. So let's see. And some of these things also is very, very important. Okay, that's why I said we started 76. But only few of us are here. So the most punctual, okay, goes to Esther Precious Amlon. You always see her. Okay. Now, please, we have on Canvas. Canvas is able to track the attendance, and these attendance have been sharing with Charlotte. It's able to track the attendance, the time the person joins and the time the person leaves. So we went through this, able to know she's the most punctual. Okay, most punctual. So congratulations, Precious. Keep it up. Okay, to go a long way to help you. And the next one is the participating. See, when you ask person, you ask a question, you want to say something, you also want to contribute. Okay, so that is that one or that award also goes to Joshua. Okay, so Joshua was the most active participant. Okay, I have to be honest. You bagged me with a lot of questions, and yes. So Joshua, congratulations. Keep it up. Okay, always keep it up. It's good to ask questions. Don't be observing. Yes, it's good to have good observation, but whilst you're observing, you ask questions. You have to ask questions. You have to ask questions. Okay. So congratulations, Joshua. And the last is the best project. Okay, so the best project, as I said, I wish we could provide some, I mean, monetary something, but for now, we are going to hold on with that. So maybe let's give ourselves some time where some of these things will give these people an opportunity, either even, who knows, a lot of opportunities will come. So the best project goes to Team Aces. They did well, their project work, the TAs all said it. Okay, that was, I mean, fantastic. Now, as I said, you all did well, but one of the things that you have to know is you always have the best. Okay, I mean, when you are going for Olympics, you all train, but the best is the best. The best is the one who actually spend time to do the research. The best is the one who actually take or he took his time, okay, to check everything steady and came out with the best. Okay, so that is so. Congratulations to Manal and Precious. That was a fantastic project. That was a fantastic project. Okay, all right. So thank you all. This is where I will end. See you guys again. Thank you all. We had a wonderful time. And to be frank, I'm very, very happy and I'm very, very excited Okay, and as I said, I'll be happy to see all of you, those who are here in February. Okay, and February on, please, is going to be, I've started preparing the slides, and me myself, all the things that we were learning, the calculus, L'Hopital rule, Taylor's series, all those things, I was shocked to find out that they are all in machine learning. So I can't wait. I can't wait to see you guys so that we'll be able to build systems, okay, able to build systems that we can use in our local settings over here. All right. So, guys, thank you all, and I really appreciate your time, your effort, everything that you put in. Okay, as I say, your certificate will be sent to you. So those who receive award, it will be sent. So you're going to have two. But if you didn't receive any award, you are going to have one certificate. Okay, and as I said, the certificate is important. It will open door, but you need to practice more. You need to practice more because your skill is what is important, not the certificate. Let me stress it again. The skill is much, much more important than the certificate. Get a certificate is fine, but you need to have the skills. Okay, that will keep you. All right. So, guys, thank you. Thank you. And Merry Christmas to you in advance. Let me say Merry Christmas in advance. So, and also Happy New Year also in advance. I'll see you guys February lane next year. All right. But we can still chat on our platform. If you have any issue, you can DM us. Okay. All right. So, bye.
Hello.